you guys have any more questions, feel free to type them in before other people show up so that we go over the stuff that you want to go over. So ideal gas law, sig figs for adding. Anything else you guys want to talk about? All right. We'll talk about the sig figs first, just so that when we do all the other problems, we know what the sig figs are. Right. So adding sig figs, so the easier sig figs is multiplying and dividing. So for the rules about sig figs, uh, for multiplying and dividing, this one you just look at all of your numbers and your answer will have same number of sig figs as the one with the least number of sig figs. So adding, subtracting, or multiplying, dividing, easy. But when it comes to adding and subtracting, this is where we care where the sig fig is. So answer will have sig fig in the least precise measurement. So what that just means, essentially, whichever number that you're adding runs out of sig figs first. So um, whichever place sig figs ends first. So whichever place sig fig ends. So when we talk about that, we could think like hundreds, tens, ones. Then this is the tenths, hundredth, and then like the thousandth, so on and so forth. So when we add numbers like this, where it's like 120 plus 11.3 plus 0.02 plus 1.8, like this. If we do our normal math, this is what, 2, 11, 3, 3, 1. But then I have to check where my sig figs are. So for this first number, the 120, it ends in the hundreds place right here, or the tens place, because that 0 doesn't count. For the 11.3, it ends in the tenths place, so it ends right there. For the third number, it ends in the hundredths, and then the 1.8 also ends in the tenths. So if we looked at where all of these numbers would end, so if we looked here, it would capture all of that. These would capture up to here, and then the 120 would capture up to here. So essentially the one that is the least precise, which is basically where it ends first, and in this case it'd be the 120. Since the 120 ends in the tens place, we only care up until the tens place. So I want to keep the 1 and the 3. Then I just have to see what I have to do with this one. So this one, I would keep it. I would have to round down, so that my answer would be 130. So the sig figs would just be in the hundreds and the tens place because of this. And then we still need a place marker because this is in the tens place, this is the hundreds, so we need a place marker 0 right there. Someone's trying to get in, but they can't. So that's sig figs. All right. So the first couple of minutes, just a quick review of sig figs. All right, and next, the ideal gas laws. So, ideal gas law is Pvnert, or Pvnert, PV equals nRT. And since it's the ideal gas law, more importantly, it's this R value. The R is 0.0821. Well, let me send another request. And since this one will have very specific units, so we got this from putting everything in STP values. So now anytime we do math, since the R value has these units, we have to make sure that pressure is in atmospheres, volume is in liters, N is mole, and T is in Kelvin. And then that's pretty much it. So, practice problem. Someone's trying to get in, but they cannot. If there's a gas ready, set, go. Try this out. Oh, shoot. A bunch of people are trying to get in. But now you're all in. Perfect. That's weird. But now I know what that symbol stands for. Congratulations. We basically just started. So try this ideal gas problem for all of you that just got in. Thanks, Stuart. Anyone done? Actually, I didn't do this problem yet either. Units. What units? $38.3 moles. Let's see. It's currently going ideal gas. Balance equations. Yeah, I don't know where 38.3 came from. I don't know where Alec is just saying G, but I also got 1.42 grams and 0.0508 moles. Cool. So yeah, so if you guys have questions, feel free to type them in. Remember, I don't have any of the homework, so if you guys just saying, hey, do number 4, do number 2, I don't know what you're talking about, so you have to type it all out. So let's go over this one. And if you look to the left of the chat box, there should be a running timeline of what we're talking about. So anytime you do have a question about something, if I see it, I'll type it in just so that you could see, okay, oh, Mr. Lee is going to go over balancing equations. So you don't have to like constantly type it in. All right, so this is ideal gas law. So we need to use the ideal units. And we know it's ideal gas law because we're given a pressure, a volume, a temperature, and we want to know number of moles. So I'm given a pressure, 843.24 torr. We're given a volume of 1, 2, 3, 4 milliliters. And we're given a temperature of 55.6. And I want to know number of moles. So this is, hey, look, I see a P, V, T, I'm looking for N. Perfect. Ideal gas law. So I have to change Tor into ATM. And that is 1.109 dot dot dot. So my new pressure is 1.109 dot 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 ATM. My volume, I just moved the decimal point over 3. So that's going to be 1.234. Temperature, I have to add 273. And that's going to get us to 328.6 Kelvin. And now we have to look for moles. Can you go to the problem H, blah, blah. Did the pop? I don't know. I thought Tor and ATM were the same, so that messed me up. Oh. Tor and millimeters of mercury, those are the same ones. So then, at this point, you really just plug stuff in. So PV equals nRT. I'm going to move this. So we know the pressure is 1.109 dot dot dot. We know the volume is 1.234. We're looking for N. We know R is 0.0821 and temperature is 328.6. Perfect. Thanks, Aiden. Then, just a little bit of algebra. We're going to divide both sides. So I'll do the next part in different colors. Like, oh, this is me solving the work. 328.6. So I'm dividing both sides by 0.0821 and 328.6. Some of you like to do the math before, and if you did the math before, it would become what? A times 1.234, 1.369 dot 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 over 26.97 dot dot dot, and then so the number of moles would be 0.0507 dot 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 moles. So that was the answer for my first part. So how many moles? And I have to check sig figs real quick where, hey, my pressure had 5, volume had 4, temperature ended in the 10th place. So I want this to the 10th place. So that's 4. So the correct number of sig figs would be 4. So Aiden's sig figs were actually off. So then my answer would be 0.05075 moles. N2. And then to go from moles to grams, you just convert those moles into grams using molar mass. Let's get rid of all this. So how come it's not 3 because of the R? It's not 3 because of the R, because since R is a constant, we don't care about those sig figs. So yeah, so anytime you're using a constant where it's given to you or it's like a known value or it's on the periodic table, we don't take into consideration those sig figs. Then the last step would be to just convert. So we have our 0.0507 moles of N2. Then to get rid of 1 mole of N2, there's 28.02 grams, which would give us 1.422 grams of N2. 1.422. All right, let's look at that. If say blah, blah, how come it's not 3? What's the difference between ideal gas and real gas? Why is the ideal gas law ideal? Why wouldn't the temperatures also affect the sig figs? Temperature did, but remember, when we did the math, we didn't use Celsius. We used Kelvin right here. And we got that Kelvin by adding, right? And when we add, we only care about where the sig fig is. And in this case, the sig fig ends in the 10th place. So when I add the 273, the Kelvin should also end in the 10th place. So that's why the Kelvin actually has 4 sig figs. Volume has 4, and then pressure has 5. Alec, they still do bump into each other, but they have elastic collisions. This is when we tell Yusuf, hey, note 7.1, literally like the first 3 slides. So ideal gases, they do bump into stuff. They have elastic collisions, meaning they don't lose energy as they bounce off. Real gases would slowly start to lose energy as they bounce around. All right. There's a bunch of other stuff you have to know. Difference between ideal and real gases. That's just one of them. So what I'm going to do is, if you guys want to spend more time on the ideal gas laws, the little poll to the bottom left near the chat box, vote yes or no if you want to stay. So do you want more time on this particular topic? Then we'll stay. And then if majority of people think they're good with ideal gas law, then we will move on. I'll give you like 10 seconds. What was the threshold that I did last time? 75%. Is that a super majority? Is that too much, or should I just do simple majority? Simple majority. All right. Out of the people that voted, 60% of you said no, no more time needed. So we're going to move on. So 5 minutes to 24 minutes, we talked about ideal gas law. And then we'll talk about Car's question. 2 hugas. Hydrogen gas. Got it. And I think Nicole asked balancing, so we'll practice balancing here. Hydrogen gas plus oxygen gas makes water. Then if all the gases were measured at 1 atm and 25 degrees Celsius, what volume of hydrogen would be needed to react with 3.5 liters of O2? Okay, blah, blah. Can we talk about the density of gas? That'll be after grams. All right. Couple things. So typically, probably on your test, you'll actually just be given the sentence. You won't be given this. So I could write something like Hydrogen reacts with oxygen to produce water vapor. And then I could ask you the question where it would ask what volume of hydrogen is needed to react with 3.5 liters of oxygen if at 1, let's say 0.00 atm and 25.0 degrees Celsius. So then you'll get a question like this. So the first thing you have to be able to do is at least write out the compounds that are involved. So hydrogen reacts with oxygen to make water vapor. So at least you know this part is going to be my forward arrow. Water vapor is like, okay, I know that at least. H2O, gas. Hydrogen reacts with oxygen, so definitely a plus. And this is the part where you have to remember a couple things. You have to remember the diatomics that never have fear of ice clear beverages. So that means when we're talking about hydrogen, we're actually talking about H2, and that's a gas. And then oxygen, O2, also a gas, like that. So now we have the reaction written. We have to balance it. And typically when I balance, I just start from the left and balance my way to the right. So I look here, I have 2 hydrogens. So the blue is just me showing my work. Okay, there's 2 hydrogens there, and there's 2 hydrogens here. So hydrogens seem to be good. Then, so I move on to the oxygen. So essentially when you're balancing, you just want to remember you're making the left side equal to the right side, the number of atoms. So I'm counting each individual atom. So then on this side I have 2 oxygens, but in this case I only have 1 oxygen. So when it comes time to balancing equations, once you write the chemicals, you can't change the chemicals. Meaning, if I wanted to balance this, I can't add a 2 here. Because that's going to change what the compound actually is. So what's the only thing you can change are the coefficients. So that's the number that goes in front. And since right now I have 2 oxygens here, but only 1 oxygen here, I need 2. So now this becomes 2 oxygens. But now at this point, I've also changed the number of hydrogens. So instead of 2, there's 4 hydrogens. And if there's 4 hydrogens, that means I have to make this 4. Only way to make this 4 hydrogens would be to put 2 in front of there. Then once you think you balance everything, you could just check. Okay, I have 4 hydrogens here, 4 hydrogens here, check. 2 oxygens, 2 oxygens, check. So then everything is balanced. So at this point now, since Kara's the one that asked, and Savannah's asking something similar, what type of gas problem would this be? How do you know it's stoic? Look at the chart we made. Alec, don't write the answer. I see you typing, Alec. You too, Aiden. Other problems could give you the coefficients. But how do you know this one is going to be a gas stoic? Constant temperature and pressure, okay. But what's the question asking? What are we looking for? Volume. Given volume of what though? Volume of Yeah, hydrogen, and we're going for substance A to substance B. So we want to know the volume of hydrogen, but we're given what? Oxygen. So we're starting with oxygen and we want to go to hydrogen. That's a key idea in gas stoic, where we're starting with one thing and then we want to go to a different substance. So then, since the the reaction is taking place at 1 atmosphere, 25 degrees Celsius, we're not really changing the temperature or pressure. So then you could say, hey, we're keeping this constant. If we keep that constant, instead of looking at the coefficients as a mole ratio, we could look at them as volume ratio. So now this becomes, we start off with 3.5 liters of O2. I want to get rid of liters of O2, and I want to go to liters of H2. So in this case, we could go liters to liters because they're both gases, and there's a constant temperature and pressure, and we have a balanced chemical equation. So in order to figure out how many liters of each I need, I look at the coefficients. For every 2 liters of H2, I need 1 liter of O2. So liters of O2 would cancel out, leaving us with 6 plus 1. 7.0 liters of H2. Yeah. So you might have gotten tripped up because it's like, okay, they gave me a pressure, temperature, volume, and a volume. So you might have tried the combined gas law. But the key thing here was that, hey, we're starting at O2 and we're going to hydrogen, a different substance. All right, so let's see. Graham's law will be after Dalton, so this was just a problem. Come on, Jerry. 24 to 34 minutes. What did we just talk about? Practice problem? All right, someone tell Kara what STP is. The balloon popping question. This is what we'll do. We'll do all the homework problems at the end. So, balloon popping. And what is standard temperature and pressure? Perfect. So, Dalton's law. Dalton's law is all about total pressure is the sum of all the partial pressures of a gas. So Dalton's law would be like pressure total is going to be the partial pressure of gas 1 plus partial pressure of gas 2 plus partial pressure of gas 3 plus yada yada yada. So that just means like in a container, if you have a bunch of different gases, like gas 1, 1, 1, 1, 1, 1, 2, 2, 2, 2, 3, 3, 3, 3, if you add up all of their individual pressures, that's going to add up to the total pressure of the entire container. And another version of Dalton's law would be what we did for lab 5. We collected a gas over water. So in this case, Like in our lab, we collected gas over water. So that means this is going to be the pressure total right here is going to be the pressure of the gas we're looking for plus pressure of water. Yeah, I remember. Then this is when you have to use the water vapor pressure chart where the pressure of water is based on the temperature. So if you use the chart, you could correlate the pressure of water with the temperature of the water. That's Dalton's law. Yeah, so if you want, let's say you wanted to find the partial pressure of this gas, you should know, let's say, the total pressure, and then if you could figure out the pressure of water, you just subtract to find pressure of the gas. So we can do a practice problem. Let's see if I can find practice problems. Just if I brought my review. Dalton's law, practice problem. How many of you have the water pressure the water vapor pressure chart with you? Perfect. Then I could do this problem. All right, let's try this. I'll change the numbers up so it's not exactly the same. Go. Oh, let's wait for others to chime in to see what they got. I guess it depends what units. But since Car didn't give us a unit, we don't know what unit she's in. All right, let's try this. Seems like you guys are all getting similar answers. Most of you. All right, so keywords here is definitely collected over water, partial pressure, total pressure. So the total pressure is going to be pressure of hydrogen gas plus pressure of H2O. And didn't convert. So then key thing here is to make sure that your pressure units are the same. So pressure total is pressure of hydrogen plus pressure of water, which I have to look at the chart. How hot is water? 20 degrees Celsius. That is 17.5 millimeters of mercury. And then depending, most of you guys converted it to millimeters of mercury, so let's change it to millimeters of mercury. So since this is in atmospheres, this is in millimeters of mercury, we can't just straight add them yet. So we have to convert the 1.9769 ATM. For every 1 ATM, there's 760. Mama hug. 1.9769 times 760, that's 1502.444. And then we will finally add them together. So plus 17.5. You get 1519.944. Now the fun part to figure out sig figs. Correct. But we'll see. So since 1, 2, 3, 4, 5 sig figs when we're adding and subtracting. 1, 2, 3, 4, 5 sig figs. So, and we don't care about the 17.5 because this was from the chart, so it has technically infinite number of sig figs. This one has 5 sig figs. So then it's going to go to the 10th, which means my answer would be 1519.9 millimeters of mercury. All right, so that's Dalton's law. Shall we move on? Let us clear all your answers. 10 seconds to figure out if you want to move on or continue with Dalton's law. $10,000 place. So correct. When we're adding, we care about where it ends, but we have to remember where we came from. So this number, if we did the math, it ends right here, right? But we got this number from our original atmospheres. So in order to go from atmospheres to millimeters of mercury, we multiplied. So that's why we counted 1, 2, 3, 4, 5 sig figs. So we only care about 1, 2, 3, 4, 5. So the first 5 significant figures, which in this case ends right there. Then, since we're adding, that's when we care about where the sig fig ends. So in this case, it would end with the 4 in the 10th place. So that's why it ends in the 10th place. So sig figs kind of get confusing, especially when you're doing multiple different math operations. Like you're multiplying, dividing, then adding and subtracting. So then you have to juggle those two sig fig rules. And since more of you want to stay here, so let's do more practice problems. All right, do this. And for those of you that have questions on the homework problems, we'll get those at the end. Balancing. Balancing is tough to go over just because there's no real trick to work on it. But if you want to watch the GVL about balancing, there's a GVL where we practice a lot with balancing in first semester. I think it's unit 5. So if you want to practice, yeah, unit 5. So there's a GVL if you want to focus on balancing equations. That's the one when you'd want to go back to. Ooh, 2 different answers. Oh, same answer. Technically, no one has the correct units. Still, technically, no one has the correct units. Because that's technically correct. All right, let's see if those are equivalent answers. Yes, they are. All right, so it seems like you guys are all getting similar answers. Granted, there's 1, 2, 3, 4 of you, and some of you live together. So, keywords here: partial pressure, total pressure, and then a bunch of different gases. So pressure total is pressure of CO2 plus pressure of nitrogen plus pressure of oxygen. And we want to find oxygen. Couple things that we have to make sure. You have to identify, hey, this is atmospheres, torrs, millimeters of mercury. So we have to make sure all of our pressure units are the same. I'm going to change it to millimeters of mercury just because torr and millimeters of mercury are the same thing. Yeah. So this, I could just rewrite it as 0.285 mmHg. But I do have to convert the total pressure. So the 1.04 atm for every 1 atm, there's 760 mmHg. If you found it in ATM, the answer should still be the same. You just have to convert it a little, so no worries. 790.4 mmHg. So now if we start to plug in some numbers, this is 790.4 equals 0.285 plus 593.25 plus pressure of O2. Then at this point, definitely don't divide or multiply. You are subtracting. So then 790 minus the 0.285 minus 593.25, you get 195.865 mmHg. But now we have to check sig figs. Sig figs here, 3, so it ends in the 3 past the decimal. For the nitrogen, it ends 2 past the decimal. Then for my ATM, if you look, I started off with 3 sig figs. So that's why when I converted it to millimeters of mercury, I need 3 sig figs here, which ends in the ones place. So now if we compare the 3 past the decimal, 2 past the decimal, and in the ones place, the ones place ends first. So that means I want my answer in the ones place. So then my answer would be 196 millimeters of mercury, capital H, lowercase g. And if you did it in atmospheres, you should have gotten 0.259. Partial pressure of oxygen. This must be Andrew Keller. All right, so that's another Dalton's Law problem. Good or move on? Time to vote. Ready, set, go. All right. 80% says to move on. So we're moving on. 34, 2, 53. That was Dalton's. It says you're going to specify the units. Yes, so that's easier for you guys to figure out which one. If we have time, we'll go to balancing equations. So Graham's law. I keep getting a 196.865. Good job, 196.865. Did I write it wrong? Oh, I did. You're right. It's supposed to be 197. Good job. Everyone else just blindly followed. A plus for Aiden. And Preston. So it is 197. You're right. All right, so Graham's law, plus 200 points, indeed. Graham's law. This is the only one that deals with velocity. So Graham's law would be m1 v1 squared is m2 v2 squared. And the velocity is the only one that's being squared. A different version, if we were to solve for how many times faster something is, like if we said gas 1 was faster, I could replace that with m fast v fast squared equals, I guess that's going to confuse you guys. Yeah, you could put the halves there, but if you think about it, the halves really cancel out, so you don't need the halves there. But you could leave the halves there anyway, but eventually they would cancel out. Equals m slow v slow squared. Then a little bit of math. This becomes v fast squared v slow squared equals m slow m fast. Then square root, square root. So this is the other version of Graham's law where after you find this number, right here, that number is how many times faster gas fast is. So two different versions of Graham's law, 1 and then 2. So yeah, anytime something says velocity, that's definitely Graham's law. So now let's practice. Try this. Change up the gas. Ready, set, go. (332 meters per second). Let's see if anyone agrees or disagrees. I am indifferent. Wrong answer. I'm confused. 279, 332, 332. I'm confused. All right. Sounds like I have to go over stuff. All right. We need help on the lab. What time shall you be there tomorrow? Since tomorrow's the regular start, I'll probably be there by 7:10. 7 o'clock, around there. Speed represents velocity. The m is like the molecular mass of the two things you were given, if I remember correctly. In this case, molar mass of butane and argon. Correct. Graham's law. mv squared equals mv squared. So let's just say this side's going to be argon, this side's going to be butane. So I have to figure out the mass of argon. Mass of argon is 39.95. So 39.95. And the velocity of argon is 400 decimal squared. Equals, I know I could find the mass of butane. That's going to be 58.14 grams per mole. So that's 58.14 times V squared. So I'm looking for how fast butane is compared. Then I'm going to divide both sides by 58.4, so it'll be V squared equals 39.95, 400 squared over 58.14. Then if I do math here, well, I'm going to just square root that, square root this. This equals V. Someone help Alec out. So then the top number becomes 6392,000 over. So I'm just showing a little bit more work so that you could follow along with your numbers. And then correct number sig figs would just be 3, which is 332 meters per second. Because the R is liter atmosphere per mole Kelvin. Correct. So hopefully for those of you that got this or didn't get this, you see where you went wrong. A lot of times it's just because people forget to square something when they should have squared it, or they just did math wrong. All right, so that's Graham's law. Do y'all want more time on this? Ready, set, go. All right, and it seems like 75% of you do not want extra time on this. So we will move on. All right, Dalton's 53 to 1 hour 05 minutes plus grams. Anyone here get the answer to number 12 on the homework? Wow, Alec, not everyone is in my class. Gosh, just kidding. Only two of you aren't in my class. And the other two are in Lockman. Oh, I should probably add Helm back. Because technically Lockman is Helm. I'll do that later. Oh, actually, yeah. No, leave the... What? Alright, next thing we're going to talk about is gas density. Gas density. So density of a gas, since the temperature and volume, or volume is affected by pressure and temperature, density of the gas will be the pressure times molar mass over RT. And since in this case we're using R, liter ATM over mole Kelvin, temperature has to be in Kelvin, pressure has to be in ATM, and then molar mass will be grams per mole. And anytime you solve for density, it'll usually be left with grams per liter. Who can help Jay out? Who can confirm or deny his statement? Do I have any density questions? Confirm. Can confirm. Yep. Okay. Thanks. Look at you guys, also helpful. Ready, set, go! One person with an answer, another person with an answer. Two different answers. Can only be one. Who's it gonna be? No, be confident in your answer. Trust yourself. All right. Keyword here is density. So density of a gas is pressure times molar mass over RT. The pressure is already in atmosphere, so that's good. But the temperature, we have to add 273, which is going to be 298 Kelvin. Then the molar mass of CO2 is 12.01 plus 16 plus 16, which is 44.01. So the density would be the pressure, which is 1.25 atmospheres, the molar mass, which is 44.01 grams per mole, over 0.0821 liter atmosphere mole Kelvin times temperature, 298 Kelvin. ATMs would cancel out, Kelvin cancels, mole cancels, leaving you with grams per liter. Oh, yeah, so this one you didn't have to convert the pressure. See you later, Alec. So then 1.25 times 44.01. I'll just give you some in-between steps. Hopefully, if you are punching this into your calculator, these numbers seem familiar. Whoa, what's going on? 2.24854 dot dot dot. And in this case, we only want 3 sig fig, so we 2.25 grams per liter. Did I earn my trust again? Yes, yes you did. Oh, that sounds like a Justin Rush then. All right. Stay on this or move on. Let me know. 10 seconds. A lot of this stuff is you just being able to figure out which gas law and making sure your units are good. The skill wise isn't too difficult because it's just really it's plugging stuff in and figuring out the answer. So 10 more seconds to vote. And then we'll see what you guys all want. And it looks like you guys want more practice problems. All right, let's do more practice problems. I'm going to change it up a bit. Ready, set, go. Oh, that's just like general density, mass over volume. So I wrote that because that's how you typically find density of anything, but the volume of a gas could change based on pressure and temperature. So we couldn't use volume to find the density. So we had to change it up. 252 kilopascals. I need more practice on this one because I am confused. Good thing you're practicing, right? I hope. Anyone else get an answer? Are you still working on it? 1.74 kilopascals. Is a gram over liter the pressure? Thanks, Aiden. Anyone else get an answer? I like to have at least a couple people agree. As of now, we have two different answers. All right, I'll start counting you down. Perfect. If you're stuck, that means you're glad you're here so that you can practice. Let's see what other people get, then we'll try to get you unstuck. 3 different answers. All right, I think it's time I step in and that we go over it. All right, so let's see what y'all did. So, density is pressure times molar mass over RT. Then we'll see where you guys messed up. Couple things. Temperature has to be in Kelvin, so 273.35.2, so 328.2 Kelvin. So I have 1.753 grams per liter. I'm looking for the pressure, and let's see how you guys messed up on the molar mass. Molar mass is 38.00 grams per mole. Then we have our 0.0821 liter atmosphere, mole, Kelvin, and then our temperature is 328.2 Kelvin. Kelvins will cancel, mole will cancel, liters cancel, grams cancel. Then we have to do a little bit of math, so I'm going to cross multiply, so this becomes 1.753. Ooh, I figure a couple students forgot about diatomics. 0.0821. Anyone else forget about the diatomics? Then divide both sides by 38.00. 1.753 times 0.0821 times 328.2 divided by 38. Pressure equals 1.243 dot dot dot. But this is in atmospheres. Did nobody get the right answer? So we have to convert the atmospheres into kilopascals, which is 101.3 kPa. So the correct answer is, I don't think anyone got it. Yep, nobody got it. 125.91 dot dot dot. Sig figs, we go back. This had 4. We don't care about this, don't care about this. This one had 4, so answer is 125.9 kilopascals. Remember, sometimes I could do stuff wrong. Can I do that slower? All right. I'll do it in pink. So first thing I did, I set it up. So density I got from here, 1.753. The pressure I'm looking for, so that's why the P's there. The molar mass I got from F2, because that's a molar mass of 2 fluorines. R is just the constant. And then temperature, we converted the Celsius to Kelvin and put it here. Pascals and kilopascals are different. There's 1,000 pascals in a kilopascal. So if you're thinking about pascals, then there's 101,300 pascals in 1 atm. Kilopascal, there's 101. Then Kara, what I did, I essentially like cross multiplied. So that's why it's the 1.753 times 0.0821 times 328.2. So that's why these numbers are right here. And then I kept this the same. So that's the P times 38. Then I had to divide both sides by 38. And that's how I got that 1.243. And then convert it. Why divide by 38? Because right now it was pressure times molar mass right here. So pressure times molar mass right here. So then since I'm solving for P, I need to get rid of the 38. So in order to get rid of this 38, I have to divide both sides by 38. All right. Move on or good. Ready, sit, go. '60-40. All right. Looks like we're doing another practice problem. This will be the last one. Do you guys want a problem similar to this? Or do you want to solve for density? This one. Since you guys are asking a bunch, probably like at least 8 of them. Everybody needs a good grade somewhere. So that's why we're practicing. Negative 273. (702.3 degrees Celsius). 975 degrees Celsius. 702.3. Oh, look at that. Three people are getting an answer close to each other. So let's talk now. All right, so let's see what some of you who didn't get that. I think you guys got some of those answers. So density is pressure times molar mass over RT. We have the density, 2.453. We have the pressure, 2.344. The molar mass of krypton is 83.8. R is 0.0821, and you're solving for T. Depending on what you did, most of you probably would cross multiply, so you got 2.453 times 0.21, 0.2013 dot dot dot. T equals 2.344 times 83.8, 196.4272. So this number I multiplied to get together to get this and then others. Then divide by 0.2013 dot dot dot, 0.2013 dot dot dot, divided by 0.20133. The temperature would be 975.35 dot dot dot. But Kelvin, so we have to subtract 273. We get 702.35 dot dot dot. And correct sig figs. Let's see, 4 sig figs, 4 sig figs, 4, 4, 4, 4. So everything needs 4, which will be 1, 2, 3, 4. So 1, 2, 3, 4. It'll be 702.4 degrees Celsius. How do you guys get 0.3? Did I do something wrong? Or did you guys do something wrong? 2.453 times 0.0821. See ya. Once we got different molar masses for krypton. Cool. All right. Wow. Density. Long time. Why is this one also taking so long? You know we're reviewing more tomorrow, right? So you guys ask me for help tomorrow. All right. Savannah's question finally. Gas stoic. She's still here? Yep, she still is. All right. Gas stoic. There's not much. Hi. Do you guys eat dinner before you come here, or are you guys like eating dinner? Like some of you have been here since 6. No, I don't eat. No, I'm eating dinner right now. Go eat. Eat a hot pocket. I only eat chemistry. Nice. Who still has Hatos? Never had one. Can't believe you never had a hot pocket. I know. That poll, that's more time. Vote if you guys ever had a hot pocket. So yes, I did have a hot pocket before in my life, or no, I have not. We'll see how many people. Gas stoic. So this one, you have to first have a balanced chemical equation, which kind of goes back to Nicole's question. Balanced chemical equation. I've had a hot pocket. Josh, there's voting stuff. You don't have to say it. Pizza one is best. Correct. The pepperoni pizza one is the best. Balanced chemical equation. Then if you're at a constant temperature and pressure, the coefficients can be used as volume ratios. So this one is a problem. Hydroxide. Ready, set, go! Oh, it's not gas stoic. This is almost stoic. Hold on, this is not a gas stoic problem. This is a normal stoic problem. Try this one first. We'll come back to this. Maybe. I'm tired. Do this. Wow. A bunch of you have never had Hot Pockets before. Carl, you never had a Hot Pocket? Savvy. Jay, I don't even know who you are, but eat a Hot Pocket. Nicole's still here. She's just quietly waiting for me to go over balancing equations. You never had a Hot Pocket either? Impressive. You guys have never lived. Let's see. What's the thing for hydrogen chloride gas? HC. Kara! Kara. Kara, what's the charge of hydrogen? Positive. Chlorine is what charge? Negative. How many of each do you need? Kara. Anyone have the answer for this? Because I'm getting tired. All right, let's go with Aiden's answer. Let's check. All the gases, same temperature and pressure. Calculate the volume of oxygen needed to produce 6.50 liters of carbon dioxide. So I should have had you guys balance it so that you guys could get more practice. But well, 6.50 liters of CO2 We want to get rid of liters of CO2 and then go to liters of oxygen. Since they're at the same temperature and pressure, we could use the coefficients as the volume ratios. So for every 2 CO2s, there's 1 O2. So this becomes 3.25 liters of O2. That's gas stoic. Questions on gas stoic? Move on or want more time? You gotta vote. All right. 85.7% of you want to move on. So let's move on. There's nothing to move on to, really. All right. So we're going to do this social experiment. Since I don't want to do this any longer. 46 minutes. You guys got to ask me one more question. So now it's time for you guys to fight over what question you guys want me to go over. All right, figure it out. Just one more question. So if you guys have a question on homework, first person to type out their homework question wins. Or whoever types in the topic first, we go over that. Ooh, Josh comes in with the Hot Pocket question. So that's the question I'm going to answer. I think it takes like 3 minutes. All right, see ya. Just kidding. Type the balloon question. That's just a combined gas law question anyway, but feel free to type it out. You have 10 seconds. Too late. Goodbye. Type faster. How long is this question, Kara? You've been typing for like 4 minutes. All right. A balloon has the max capacity of 6 liters, blah, blah, blah. Looks like your sig figs are going to be all screwy. All right, so you have a balloon, and the max volume is 6 liters. Baloney. And the balloon was filled at a room temperature. So temperature is 22 degrees Celsius. Pressure was 785 mama hugs. And the volume was 5.75 liters. See you, Mr. J. Lee. Hey, that's my initials. And let's see. The kid let the balloon escape. It rose to an altitude of 2 kilometers, where now the pressure is 735, and the temperature is 20 degrees Celsius. So, did the balloon pop? How would we know if the balloon is going to pop? Too much pressure? Well, granted, remember, what happened to pressure? Pressure went down. There's no graph on the lab. So in this case, we want to know, hey, we will know the balloon will pop if the volume is greater than 6, because the max volume is 6. So you have 2 temperatures, 2 pressures, and you're solving for V. Does that make sense now? That's easy. I just can't read. Cool. Does anybody want me to actually do this problem? Or should I just sign out now? Yeah, that works. Sign out? No. Do it. Do it. Can you do it? Hey, Kyle's back. All right. So this one is the combined gas law. We just want to make sure our pressures are the same unit, volume same unit, but temperature has to be in Kelvin. So plus 273. That's 295 Kelvin plus 273. That's 293 Kelvin. Then we just plug a bunch of stuff into a bunch of different numbers, and then bada bing, bada boom, you get your answer. So first pressure was 785. Volume was 5.75. They got real close to that max capacity of that balloon. Temperature is 295 equals pressure 735 volume over 293. Then let's just multiply out the numbers. So this side becomes 15.300 dot 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 equals 735 divided by 293. This equals 2.5085 dot 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 V. Then and you get a volume of 8,170. That's not right either. How'd you get 8,170? Setup is the same. Did you end up getting these numbers? And then did you divide both sides by 2.5? Because I got what Kyle got, 6.10 liters. So what happened? Did the balloon pop or not pop? The balloon popped. Did you get? All right, cool. Decimal is important. Bonjour, Lee. Adios, people. This was a long one. This was just as long as the final review. Why? I don't know. Final review was 1 hour longer. Was it? Final review was close to 3 hours? Oh, just kidding then. Well, I'm gonna end this recording.